Yeah, thank you, Brendan. So, hi everyone. Can everyone from Dortmund also see me and see the slides? And hear me?
Yep.
Okay, yeah, I see a thumbs up. Perfect. All right, yeah, the title is pretty long, but I think it was a really good setup with what Raphael introduced us to Trustworthy AI and the topic itself. So the overall topic, now we're diving into one specific testing tool for testing particularly one dimension in AI trustworthiness, that is robustness, reliability, and also partially explainability. So Raphael explained really all the dimensions and then touched about topics that would cover all dimensions. Now we're diving into one specific topic. Is it just the yeah, perfect. Okay, now it works. All right. First, I'll just have a small background about me and then where I'm working from. So I'm at the Fraunhofer IAS Institute in St. Augustine. So that's between Bonn and Siegburg, pretty close to here. If you don't know Fraunhofer Institute, it's basically similar to Max Planck. They're somewhat state-funded, but there is also a lot of industrial collaboration. And the goal is really knowledge transfer from research directly to the industry. And there are around 800 researchers at our institute. So at the campus, there are 3 different institutes there. And each Fraunhofer Institute in different cities has their own specializations. The Fraunhofer Institute in St. Augustine, so the IAS Institute, has been working on machine learning, data science, and AI topics since 30 years. So the specialization is really in this field. And I am part of so I'm a research associate in the AI Assurance Assessments department. This is a very new department at Fraunhofer, and it's basically led by Maximilian Partschkin. You saw in Raphael's presentation towards the end, this AI assessment paper that was developed by our department head and our team. And yeah, so the reason this department was created is because the topic is becoming so important: trustworthiness, how to evaluate AI models, how do you regulate models, and so on. Since the topic is so interesting, and so there's a need from the industry on how to do this, how to research in this area. There's now an entire department, focused on this topic. And I've been now working before in the team and now in the department now for 5 years, and I'm pursuing my PhD, and I'm close to finishing basically in this topic of developing testing methods for AI models. And during these 5 years, I've been involved in a lot of publicly funded projects, which I will also talk about these projects now. They've been in the direction of autonomous driving, autonomous trains, AI in aerospace. In all cases, not really developing the tools for doing these tasks, but really developing the trustworthiness methods to ensure that the tools are working correctly. And my research has also been progressed through these publicly funded projects, but I've also been involved in various industrial projects where we then do knowledge transfer from the knowledge we gained in these projects directly to the industry. Okay, so the agenda for today is basically, I will give you a deep dive into one of the projects that I worked on called KI-Absicherung, and how basically the automotive industry sees developing safety argumentations for deep neural networks. And from that, then I will jump into systematic weaknesses, which is basically one problem statement that the safety argumentations will want to address. The systematic weaknesses topic is basically a research paper we wrote this year. So I structured the presentation also in the same direction. So I'll have a quick introduction on what systematic weaknesses are, what related works are doing in this area, and what we proposed with our method. And then the evaluation is basically on synthetic data and real world data. So let's dive in. So the KI-Absicherung project was started in 2019 and was a 3-year-long project. It was basically consisting of all of German automotive industry except Mercedes, but they were involved in other related projects, and was a pretty large project as well. It was with a budget of 40 million euros. The goal was, using only synthetic data, how do we develop a safety argumentation for a computer vision model tasked with pedestrian detection? So if you think about, so Raphael talked about trustworthiness from the perspective of users and companies, but now let's only focus on companies itself. Let's take this phone, for example. There were a ton of tests performed at hardware level, software level, addressing various failure modes to make sure that this phone works as intended, so that basically the company can say, I can guarantee that this phone will work for 1 year, 2 years. If not, I'll repay it. The same thing does not exist in AI products, because we don't know when they'll fail. And that's what this project wanted to address. So if you boil down autonomous driving to purely computer vision, so there's no path planning, there is no locomotion and so on. You just want to do pedestrian detection, let's say bounding box detection. How do we ensure this thing works? And the way they approach this is basically by bringing together these two lands. So the perspective they had was, we have this AI land where all the AI researchers are. So they're experts in their field, they develop the models, they know about pre-processing data sets and so on. And on the other side, there are safety experts. So for example, Volkswagen, Bosch, there are already lots of safety experts working on traditional products like washing machines, cars, and so on. They know how to build safety argumentations, assurance cases, and so on, to say that this product works as intended and without failure for so and so years or so and so cycles. So they have the expertise there. And what they tried to do was bring this knowledge and that knowledge to bridge this gap between these two. And one of the approaches that finally in the 3-year-long project, so the project is over now, and there is actually a very good video on it on YouTube if you want to check out what the overall project was. But the final conclusion that the project took was basically, we need to understand what are AI-specific failure modes, and then try to address them individually. And for addressing them, what we would need is specialized testing methods to see if we can detect this failure mode in an AI model, and then a specialized method to fix this. Once we detect the failure, to fix the specific failure mode so that we have an improvement in the model. So this is what they tried to do. So to reach this model is trustworthy state. And now in this case, I'm really talking about trustworthiness purely from reliability. So back to again, Rafael's presentation, there would have been more things that should have been considered here, but we really focused on the reliability and partially also explainability. So if you only focus on these things, if you want to say model is trustworthy, so first you have to say model is robust. And for that, what do you have to do? So model has to be robust against, let's say, input perturbations, against domain shifts. I'll get into what they mean in a slide. And then model is secure against attacks. What does that mean? Model should be secure against backdoor attacks, against adversarial attacks, on. So you're identifying or going into granular level about what potential failure modes could be. And then these two steps, identify the presence of failures with testing tools and addressing failures with mitigation methods. And that these are two basically, this is how we basically split the task itself, so that now you can, like a focused and targeted way, do research in these specific problems. And in general, addressing some of the problems might actually address other problems as well. But the advantage of going into this granular level is that you have a really structured way of saying, I have now fixed systematic weaknesses, I have now fixed against input perturbations, I have now really built a robust model because I've addressed all individual failure modes independently. And like I said, so the focus of the presentation is really systematic weaknesses. That's also why I highlighted that in bold. But let's really look at all of them just to get an idea of what I'm talking about. So here's a picture from a Cityscapes dataset. It's a popular computer vision dataset for autonomous driving. What can go wrong here? So I'll try to move this a little. Yeah. What can go wrong in this example? So you want to test the computer vision model. So purely only the computer vision model, nothing else about the autonomous driving car. So this is probably even a scene from Germany itself. What should I consider? So first, robustness issues. I could have noisy sensor. Maybe so my sensor got damaged. The camera always gives you grainy pixels. That could lead to, because the camera is the first step. So you have the camera collecting the data, then there's an AI module later on somewhere that is now interpreting what the camera sees. If the camera already captures noisy data, then your model might not be robust enough to interpret what is being seen. That's one issue. The other thing is you might have trained your model in, let's say, only in Germany. Now you take your car and you want to sell this in China. That's a completely different data distribution you're putting the car in. And this is also a robustness issue, or it's a generalization problem, where if your model was not robust enough, it might not generalize to the new domain that you have put your car inside. That could be an issue. And then there's a security issues. You've probably seen this famous adversarial attack examples where people put on specifically targeted stickers on stop signals, and the car does not recognize this as a stop signal anymore. So there could be potentially adversarial attack stop signals or traffic signs, or you don't even have to attack the environment. You could probably, so if you have a car parked somewhere, someone could put a specially designed filter on your camera, on your car camera, and now onwards your car will detect things wrong, like targetedly. That could also potentially be an attack. So these are security issues you have to deal with. And now finally, another part of robustness issues is what happens. So let's say we fix these two problems, but there potentially could be situations where you are doing pedestrian detection. Maybe your model, because you don't know what's happening inside the model, these are all black boxes. Maybe your model just learned that all pedestrians are always on the right side of the image. And it's very good at detecting pedestrians on the right side, but if there's a pedestrian on the left side, it does not detect them. And because we always evaluate models on test data sets, so the traditional way to evaluate machine learning models is you have a training data, you train a model, then you have a test data set, you calculate some metric like accuracy, precision, and recall. And then if the value is good, you say, I have a better model than someone else. That's it. But you wouldn't know if your model is particularly only detecting people on the right side of the image and not on the left side, or maybe your model only detects people with blue shirt but not black shirt, because that's how the training data distribution is. And you didn't know that because you did not have a deeper look into how the data set itself was distributed. So these are potentially situations where your model has a systematic bias. So it is good at detecting some things, but it is systematically bad at detecting specific other things. And this is a very dangerous situation because such a failure would only occur in specific cases, but it will occur in all the cases where this happens. So if your model is particularly bad at detecting, let's say, blue shirt, it will continuously be bad at detecting blue shirt. But because you're evaluating your model on a global level, so on an average metric on the entire test data, you will probably not detect it, and this could lead to potentially dangerous situations. So it is of our interest to also fix this problem, so this particular failure mode where you're trying to find out if your model has this systematic weakness or bias. I think Right, what did you do?
You just click on the screen again.
Yeah.
Just go.
Okay. All right. So I didn't want to only have computer vision examples, so I bought one LLM example as well, but this is the only slide with LLMs afterwards, so we'll get back to computer vision again. So let's take the same situation, but now with an LLM. So let's just say ChatGPT. What kind of issues? So one thing you have to remember is the chatbots are hard to test traditionally because they don't have any specific task. You can use them for talking about writing a letter, or actually a doctor asking about writing a report about a patient. So there are different use cases you can use the chatbots in. And we have even a white paper from our institute about how can you test LLMs or foundation models. And our proposal at the first step is you have to assign a task to them. You need to tell where you would use the LLM. Only then can you actually test it, because then you know what you have to test about. So let's say we're using the LLM for a specific use case. It's a coding assistant. Now, again, similar to what I had with the computer vision example, the model could fail because of unusual or unspecified prompts. That's just a robustness issue similar to basically sensor noise. You're just not clearly defining your prompts or not writing them in the correct way. And if the model is not powerful enough, maybe it fails there. And then there is security issues like prompt injection attacks or data poisoning, which you probably also heard of, where people try to get past the safety filters of the models by performing specific attacks like prompt injection. But about systematic weaknesses itself, the model could be, so the model is learning on internet scale data, but the internet scale data might also be particularly biased or distributed in such a way that if you wanted to have a coding assistant, it might be very good at Python because there's a lot of repositories online about Python coding, but maybe some unknown coding language will just have very little information. So the model will not be good at it. It might have library bias where it will be very good at the popular libraries because these are also utilized more often, but will not be as good as utilizing the smaller libraries. And handle similarly popular frameworks. It could be very good at following styles that are common coding conventions, but not exclusive to company coding styles because it would not know the company coding styles. So you have this biases that the model could have learned from the training data, and that would continue during the inference time. And you want to identify them, similar to the computer vision case. you would not identify them if you just do general testing. You would need some specific testing tool that would particularly identify if my model is particularly biased or systematically weak against one of these cases. And this is what you want to find out and then potentially fix later on, or at least identify and know that my model has this particular weakness. All right, so back to computer vision. So let's now, okay, we've established the motivation. Now we want to have a deep dive in what exactly systematic weaknesses are. So the definition is, so they are semantically coherent regions in data space. They're often referred to as subsets or slices, where the performance of a DNN is significantly worse than performance on the entire data. Let's look at an example. Given inputs, so the inputs for us are, so unlike in traditional machine learning where you're training the model, in our case, as the testers or the people evaluating models, you will always get the model from someone, let's say a company, and you will get a data, or you will have to define the data space, but in general, that's also more or less fixed. And now what you're interested in is, if this is the data distribution overall, where are these regions within the data where the model will have particularly higher error in comparison to the rest of the data? And we can define what this particularly higher error is later on, but so E of S is significantly worse than E of T. And the other requirement is, so it's easy to basically find errors. You can just group all the samples that are error prone, and then you can say, I found a subset of errors. That's not interesting for us. We want to also have the slices to be semantically coherent. So they must belong or have some particular property, that they should all represent specific groups. For example, I said for the computer vision task, all the people on the right side, the model can detect. All the people on the left side, the model is very bad at detecting. In that case, the semantically coherent region would be left and right, or blue shirt versus red shirt. These are the semantical properties we are interested in, which the model should, so which we would want to identify in addition to the error of the model. And as you can imagine, that, so until here, are there any questions? We can also do the questions in between. This will get pretty technical. If there are questions, one specific thing to remember here is most computer vision data sets will not have this additional information about semantical coherence. So if you're doing object detection, for example, in the Cityscapes data set, you will have ground truth information about what the pixels are. So it's a semantical segmentation data set, so you would know what pixel belongs to what class. Or if it's an object detection data set, you would know where the bounding boxes are for different pedestrians or cars. But what you would not know is if the person is on the right side or the left side, if the person is wearing blue shirt or red shirt, if the person is a man or a woman. So these are these meta level properties that we are interested in, which would define the semantical coherence, which is generally not available. And which is also something very important if we want to find out the systematic weaknesses. Okay, before we dive into how we do it, let's see why they actually occur in, what are the origins of systematic weaknesses. So the first one, so there are three commonly discussed reasons or origins for systematic weaknesses. One is that the model is learning spurious correlations. So the examples I told until now with left and right and so on, the data distribution is such that the model, or either because of the data distribution or because of the model learning parameters, it has learned spurious correlation. So some kind of correlation, which is not what you want the model to learn, but it has learned that. For example, this popular example and data set, models learn to identify birds by looking at the sky pixels. If there were pixels of sky, it would automatically say there is a bird, even though there's not actually a bird. A similar thing was discovered also in chest X-ray images. Whenever there were chest X-rays with cancer treatment, a cancer found, there would be a signature of a doctor or something. And this model then learned to identify there's a cancer in this X-ray just because there was a signature on the side. So this kind of spurious correlation is what you don't want the model to learn, because then the model would anyway fail during inference time. That's an example from vision domain. From LLMs, there's the simple example of sentiment analysis. So people found out that models were focusing on the wrong part of the sentence to identify if it's positive or negative. So in the first sentence, the sentence basically talks about Spielberg creating positive, good movies, but in this particular case, he didn't do it correctly. But the prediction from the sentiment analysis sentence is that it's a positive sentence because it associated Spielberg with being positive. So it's looking at the wrong word to decide on the sentiment of the sentence. Similarly, in the second sentence, the sentence is basically talking about New York subway system, but it's actually being a positive sentence. But because this model focuses on the word New York subway, it automatically says it's a negative sentence. So it's like a correlation it learned. The second origin is basically insufficient data samples. And this is, of course, another classical example. People looked at existing data sets from autonomous driving or computer vision data sets and found out that certain subgroups in the data are overrepresented, for example, male or white skin color versus people from Africa or females. And this would automatically then have an impact on how well the models would perform during inference time if you deployed it worldwide. So this basically would also fall under fairness dimension because you're really looking at skin color or gender, and these are dimensions that are important from the fairness perspective. So on this broader categories of reliability, fairness, ethics, and so on, we are covering here also fairness, but it's also a reliability and robustness issue because you want your model to perform equally well without having this bias. But because the way the data set was collected and structured, the model automatically learns to be biased. And this, in the end, is a systematic weakness. And then the third case is basically an issue with noisy labels. So how the data sets are constructed again, but not now because of the distribution, but because of the labeling itself. So many large data sets like ImageNet, Celebé, and so on, in some cases, only focus on specific target labels and not the overall scene description. So if you train models on that, then it could be that you will only assign one label to this image, although there's several objects in the image. So you kind of are forcing the model to believe that there's only one specific object or high main ground object in the image or foreground object in the image, and everything else is background, which is, of course, not the correct way to train the model. And this also induces some systematic weaknesses. Or there might actually be just wrong labels in the data, which also will then lead to, if you consistently label the specific categories wrongly, then obviously model will learn to identify that incorrectly, and then you would have also systematic weaknesses later. Okay, so now let's dive into why what people have done in the field of identifying systematic weaknesses, and the field or the approaches here are called slice discovery methods, or SDMs. Slice discovery because as I said, systematic weaknesses are usually also called identifying this subsets or slices of data. So they are identifying slice discovery for that reason. There were, since 2022, a lot of papers in this direction. Primarily, these were some of the very important papers, and of course ours this year. And all of them were from pretty important institutions. So Domino, the first paper was from Stanford, the Spotlight, the SVM paper was from MIT, and so on. And there are two main directions you can differentiate between the approaches. I said earlier, one of the biggest problems with this identification of systematic weaknesses was that you don't know how to assign this semantically coherent property. So you don't know in a data set, you only know where the person, so what the person is because of the bounding box or the semantic segmentation pixels. But what you don't know is if the person is wearing a blue shirt or a black shirt, or if they're standing on the right side or the left side. This meta information or metadata, which we call, this is not available. And this is very important, of course, for identifying systematic weaknesses. And the way different papers took is basically either first performing the slicing of the data, so first identification of weaknesses, and then performing the tagging being assigning the property to the image subset, or the second approach, first performing the tagging, and then identifying what are the weak slices. So these are broadly the categories. I will give an example for each. Of course, for the second one, I'll just give our example. For the first one, let's look at Domino, this paper from Stanford. And let's dive into this already. Every approach in this field uses CLIP. So I don't know if you already know about the CLIP model. It's a model from OpenAI. It's basically multimodal. So it can do both text and vision at the same time. It has basically two encoders, a text encoder and a vision encoder, and it's been trained on also, I think, 300 million samples of images and their captions. So it's pretty good at understanding basically image and caption pairs. And almost all the papers in slice discovery methods basically use CLIP at some point because it's so powerful and it's open source. And what happens here, you perform, so you like I said earlier, you have a data set, a DNN you want to test. So this model that was provided by some industrial company, and you have a data set you want to test the model on. So you first take the data set and then you perform embedding. So you calculate the embeddings of the images using the CLIP model. So you put it through the vision encoder. And in the embedding space, because CLIP is so powerful, similar topics are grouped together. And together with this, you give the model performance outputs. So you already know you have the DNN under test, you pass the entire data through this model, you will get the performance scores. So now you have basically where the model is correct and where the model is wrong. So you combine basically the model errors with this with the semantic information in the CLIP embedding space, and then you perform clustering. And then you basically, during the clustering, you assign the task of identifying the semantic groups or the clusters which have low performance. That's basically the second step. So you're performing a slicing operation which is error aware. So first step, embed, you perform, you calculate the embeddings of the model, then you perform the clustering operation or the slicing operation. And then the third step, you explain the errors. So once you identify the clusters or the slices, then which are weak, then you want to know what is a unique property that describes this. So then you put all of these images through a language model, then you understand basically the language model will probably output something like skies without birds. That is basically saying now a description, this metadata information that tells you, okay, this is the weakness that uniquely defines this image subset, and this is the reason potentially why the model is failing. So that's maybe to go back to the slide, the first slice and then tag. So as you can see, so you've embedded, sliced, and then tagged. These are the three steps. The embedding step is just merged here. So are there any questions there? Also from Dortmund side? I guess not. Then let's dive into our approach. So this is an approach, a paper that we published this year that was accepted at TMLR, where we propose an approach now to go through the first tag and then slice operation. So let's go into the approach itself. So for us, we need three inputs here. Like I said earlier, we need the DNN under test and we need the data set. And we are actually using the CelebA data set that we also saw in Rafael's presentation. CelebA data set, if you don't know, is basically pictures of celebrities. It's like 200,000 images of celebrity faces. So we also have experiments with autonomous driving later on, but primarily let's look at the celebrity photos. And we have third input, which I did not discuss earlier, but what is very important from our perspective for our approach, because like I said, our approach falls under the tag and then slice. So for tagging, you need to know what you want to tag, what properties are important, where you want to identify the systematic weaknesses. So basically what we use is this concept called operational design domains, which was developed which is a concept that exists in the automotive research, automotive field, but for other topics, which in the KI Abschichtung project was also brought to the autonomous driving and AI side. The idea here is you define semantic dimensions and attributes that are important from the perspective of safety engineers. For example, for pedestrian detection, they identified gender, age, occlusion, distance to camera, skin color, shirt color, pant color, so on. It's everything that are required, which you think where a model could potentially have weaknesses, and also where if you have a bias, in the future, there could be problems from regulation aspects. So for example, if a model, so you trained your car and your car is particularly bad at detecting gender. So it is not detecting women as good as it detects men. That is, of course, a regulation point of view, bad for your company from the trust perspective as well. And it's just bad PR. So they identified these semantic dimensions based on what is relevant from performance issues perspective, also from fairness perspective, and is what is important from regulation aspects as well. And they also published a paper in this direction, and we basically took a subset of this operational design domain for our experiments as well. And so now you have these three inputs. And now the next step is, so we have the dimensions that we can use to do the tagging. But how do we actually do the tagging? That comes in the second step. So we have at the input stage unstructured data, because images are unstructured data. And what we want is some structured data format so that we can search for weaknesses in the model. So what we do is we convert the images into basically a tabular structure where we utilize a toolkit for metadata generation, which is basically a collection of foundation models or actual sensors, which will look at each image in our data set and then identify either if there is a person with, if it's a male or a female, what their age is, how much the occlusion is, and so on. So for all the relevant ODD dimensions, we identify what is within the data set. So you're kind of converting the image data set into a tabular data set with either true or false or Boolean operations or even more features. And in some cases, even directly from the sensor, what values we have. And this is now combined with the model performance values. So the model performance values is also similar to what we did in the domino operation. So you need to know where the model has errors. So it's always a data set with ground truth. So we already can calculate if it was a true positive, false positive, or false negative, and so on. So we combine both of them. We create a larger tabular data set, which we feed now to the final stage called SliceLine. This is basically a slice discovery method that was developed for traditional structured data sets. So what it does is it basically looks at a tabular structure. It builds a tree-like structure of all the slice combinations that you can potentially have. So at level 1, you would be building level 1 slices like gender male, gender female, skin color dark, skin color white, and so on. And then at level 2, combinations of different features, and then level 3, 3-level combinations, and so on. You build basically a tree-like structure, and you calculate how many samples fall under each of these properties and what the error within the subsets are. And it basically assigns, it also performs pruning operations and so on, because it's basically a structured search over this tree, and you want to perform it efficiently. And then it basically identifies the weakest slices or subsets in your data set. And until there, the story is pretty good. All you have to do is convert the data into structured data, you perform SliceLine, and then you get weak slices. The problem, of course, is we know computer vision models or AI models are not perfect. So there will be generating noisy metadata here. So SliceLine was developed with the idea, because it was used for structured data, that everything that you provide as metadata is correct. But we are actually giving it incorrect or potentially incorrect metadata. So how do we deal with that? And so we basically developed the first approach I said, without the consideration of noisy metadata, was our baseline, and we wanted to improve on that. So what we did is we feed the metadata also into a human evaluation step, where we only do a limited evaluation, so 60 samples per category. And then we developed a Bayesian approach so that we can correct for the errors. So based on the human evaluation results, we correct for the error within the subsets, and then that's the results that we provide as output. And I'll dive deeper into that now. So what do we mean by this Bayesian approach? So the generation of metadata with sensors is mostly, there is no errors there, but with foundation models like CLIP, there could potentially be noisy. So the identified weak slices themselves will therefore be noisy. So what we want to do is, and the origins of the data can both be data-based or noise model-based. So what we want to do is correct this observed error within the slice and bring it closer to the real error. And how we do that is basically the true error is P of E of S, and then the observed error is P of C. And to calculate basically the true error, we identified what are the important terms that would allow us to recalculate it. And as you can imagine, it's a much more complex operation if both so we have two DNN-based models within our workflow, right? We have the DNN under test, and we have the CLIP model. If they are correlated, so if they make error on the same sample, I mean, the DNN under test, the task is this a person or not? Because it's a pedestrian detection system. The CLIP model task is to do this multi-class classification. But it could be that they both make the same kind of mistake. Then they are correlated. Then you have a bigger problem. But if you assume independence, you can get rid of this part of the equation. And we identified that the only thing that you need to recalculate the true error based on the observed error is the precision values of the clip model. So in this step, all you need to do is calculate the precision of the clip model, and you can recalculate how the error should be within the data. And you can recalculate correctly what the actual slices would be, even if you had noisy metadata. So this led us to, based on, of course, the assumption that there is no correlation. Because there are some terms in this that are extremely hard to calculate without full knowledge of the data set itself. This led us to basically come up with this full algorithm where we proposed 3 methods as solutions. The first one, like I said, slice line with observed errors, so where we don't consider the noisy metadata at all. So we assume noisy metadata does not have an impact. We just do it the straightforward way. We convert images into metadata, perform slice line on that, we calculate some slices. Then we do slice line with corrected errors. That's the second approach, which I just presented now. And then we proposed SWD3, which means we just combine both of them. We do deduplication, and then we just arrange the slices based on the slice scores that they get. But basically, you're just doing a combination of these two. So these are the 3 proposed methods that we had. And we wanted to check, of course, what would be better. And the first results, so now we're back at the, how much time do I have? Oh, rush a bit. So we did experiments with synthetic data and real data. I will focus mainly on the synthetic data because it's much more interesting. We could really play around with the data. The first experiment we wanted to see was, does this really play a role? Does this noise in metadata really play a role? So what we tried to do was, so what you're seeing in these graphs are 3 bars, and each of the bar represents, the first one is the real error if you had access to perfect metadata. If you had access to, ground truth information directly. The second one is this naive approach where you don't consider the noise at all. And then the third approach is our approach where you have this correction with Bayesian approach. And what we identified was, this is basically also the upper and lower bounds for binary attributes. So if you, let's say if you had only male and female for a dimension. So you could have like a maximum value and one minimum value. And we saw that the observed error, and we also split the synthetic data into 3 categories. We had good quality data, where the clip precision values would be higher quality. We had medium quality and bad quality, where clip precision was pretty low. And what we experimented, what we want to see is, how good is the naive approach and how good is our approach at recollecting or re-estimating the true error. And we saw that for the good quality, it doesn't really matter. The observed error is as good as the real data. So you can use the naive approach. But for the medium and the bad quality, the naive approach underestimates what the true error could have been. So the naive approach is basically saying, even though this is really a bad slice, the naive approach would say, it's not a bad slice, it's okay. It is not, you don't have to worry about it. But what our approach would do is it overcorrects, but it basically recovers for all cases the worst performance. So it's not perfect, but what it lets you do is, in trustworthiness and in safety, it's better to find a non-bad slice than to let a bad slice go by, right? So you want to identify wherever potential errors could be. And our approach, even though it overcorrects, it identifies basically all the potential bad slices. And this is what we found with the synthetic data experiment. And then we also did one more experiment where we made this into now a classification problem. If you had access to potential correct data, so ground truth data, you already know what slices would have been found. So you can calculate basically the precision and recall of our approach in comparison to this ground truth information. So again, we did the same experiment with good quality, medium quality, and bad quality. And again, like I said, for good quality, it doesn't matter. You could use any approach and you get the similar results. Where your recalls are pretty high, your precision is pretty good. But in medium quality and in bad quality, so the SW3 is this combined approach that I said in the algorithm. Our combined approach recovers almost all the slices that are bad in comparison to the naive approach, which is this orange line, which is pretty bad here. So in the bad quality data, our approach significantly outperforms the naive approach, and then also it's recovering. So it's not perfectly recovering 100% of the slices, but it's recovering most of the slices that are potentially weak. And this was, of course, good news. And then we experimented with real world data sets. So first experiment was, of course, with setup A. And what you see here is basically the slices, the top 4 slices, the slice description, which tells you what are the potential weaknesses in the slice, and the statistics about how many images are in the slice, what is the error of the slice, and how bad is the performance of the slice in comparison to the rest of the data. And this is basically a parameter, of course, which we can vary as to say, if my slice performance is 10% worse than the rest of the data, then it's potentially a bad slice. And this is what I want to fix. This is also, again, this is a comparison basically to see if our approach is better than the naive approach on real world data sets as well. And we show in this table how we are recovering basically the errors. So it's still higher than this is basically the ground truth information at 0.51. And our error is significantly higher, but it's still better reconstructed than the naive approach, which just significantly underestimates the error. So that's what you see in the slide. Yeah, in conclusion, basically, so I also have experiments in the paper with autonomous driving data sets, where we took publicly available models from the internet, publicly available data sets, and then tested these models for systematic weaknesses, and then basically published about that. And we also evaluated how good the metadata quality is between GPT models and so-called GPT-V versus CLIP. And yeah, all of these evaluations are in the paper. Basically, our algorithm identifies systematic weaknesses which are aligned with dimensions that are important from ODD perspective, which is what the industry is interested in, because they want to define the categories where you want to identify weaknesses, and then search based on these categories if you have potential weaknesses or not. This is what we proposed. And then the additional noise correction leads to ensuring that safety relevant features are correctly identified. Our evaluations also show that this combined approach of the naive approach plus our proposed approach, the combined result where we do deep duplication and then arrange the slices according to the slice score, is the best approach. And also we have evaluations in comparison to SOTA methods. So this paper from Stanford and MIT, and we show why our method is better in terms of explainability, actionability, and so on. Of course, the limitations are basically where our further research needs to be done is what is really causation versus correlation. So you are finding slices within a given data set. These slices are potentially just being correlated to weak performance, but it's not really causation. You don't really know if being a woman in the image is the reason the model is bad, or if it's just in this data set, a lot of women are not detected, but it's not the features that describe the women that are leading for a model to be bad at this condition. And the other limitation is we are constrained by the ODD, so we would only find weaknesses which are defined in the ODD. Other methods like Domino do not have this problem because they are ODD independent. Yeah, that's basically it. I think I almost took all the time, but yeah, thank you for your attention. Maybe there's time for 1 or 2 questions. Yeah, thank you.